Today's teaching assistant is Lucky, but does not want to be on camera. She very much wants to go back outside with her sisters. Come on, Lucky, say hello, and then you can run away. All right. Today we're going to cover t-tests and ANOVA. So these are the first two types of inferential statistics that we're going to cover. These two are what are known as parametric tests because they have a set of assumptions that have to be met in order for them to be used. And usually that first assumption is that at least one variable is at the interval or ratio level of measurement. For t-tests in ANOVAs, that means that the dependent variable has to be interval or ratio level of measurement. On the other hand, non-parametric tests don't have to meet these assumptions. You can use ordinal data in place of interval ratio data. And we will cover some of these tests today. So with the t-test in the ANOVA family, you have a categorical independent variable and a continuous dependent variable. If your independent variable has only two categories, for instance, something like gender, where you're only using a binary version like male and female, you would use a t-test. If your independent variable has more than two categories, so you're using more cohesive interpretation of gender, then you could have male, female, non-binary. As soon as you have more than two categories in that independent variable, you use what's known as an analysis of variance, or ANOVA. So because these are parametric tests, the dependent variable has to be either interval or ratio. And if it's non-parametric, then we use what's known as the Mann-Whitney UT test, or the Kruskal-Wallis for an ANOVA. The assumptions that need to be met is that for each category of the independent variable, the dependent variable has a normal sampling distribution. So not that the actual sample is normally distributed, that its sampling distribution is normally distributed. And the way we test this is usually just by looking at the samples distribution, because as we mentioned last week, the sampling distribution is theoretical and we never actually get to see it. So we want to make sure that for all of our gender categories, our dependent variable, say it is number of pets owned, is going to be normally distributed for males, females, and non-binary individuals. So you have to check it at each level, and I'll show you how to do that in SPSS. The other assumption is that the variance within each of these categories of the independent variable is going to be roughly the same. And that's what's known as homogeneity of variance assumption. All right, so we want a normal distribution in each of those categories and roughly equal distribution of the variance. If either of these assumptions can't be met, then we either apply a penalty to the degrees of freedom so we can meet it, or we use one of the non-parametric tests. And I will show you examples of both of that. So if it sounds a little scary, don't worry, we'll go through it in detail. So there's three types of t-tests we're going to cover. One is the one sample t-test, where we just look at a sample versus the population as a whole. The independent samples t-test, and then the paired samples t-test. They're called t-tests because they use a t-distribution. So like the standard distribution uses z-scores, with the t-distribution, we transform all of our averages into t-scores and test against that. The t-distribution is a probability distribution that changes shape as the sample size gets bigger. And when it's very big, it has the shape of a normal distribution. That's why for the t-test and the analyses of variance, if we violate that assumption that the dependent variable is going to be normally distributed for each level of the independent variable, if our sample size is large enough, we don't care if that assumption is violated, right? We've got the central limit theorem that tells us that if the sample size is large enough, the theoretical sampling distribution is going to approximate a normal distribution. So if your sample size is over 100, 150 participants in each category, then it's okay if your skew and kurtosis scores aren't exactly within our -1 to +1 range. All right, so let's look at the first one, the one sample t-test. This is where you test your sample against a known population mean. Usually it's used to make sure that your sample is representative of the larger population. And that means that you have to know what the larger population average and standard deviation are. So the null hypothesis, and we're always going to use two-tailed because we've discussed the shortcomings of a one-tailed hypothesis, right? A one-tailed hypothesis is more likely to have type 2 error. So the null hypothesis is that the sample mean, which is represented here by x, is equal to the population mean, which is represented by the Greek letter alpha, mu. So mu is going to equal x. So the sample mean is equal to the population mean. The alternative hypothesis is just that they're not equal to each other. Here's an example for you. For instance, we can look at the weight of cats. One study found that cats now are heavier than in the 1990s. So what they did was they looked at a sample of cats right now from the 2020s, 2019 this study is, and they compared it to what was known about the average weight of cats in the 1990s. And they found that cats now are fatter than they were 40 years ago. Here is an example of a one sample t-test using the data from the Monitoring the Future data set. So this is what your output is going to look like in SPSS. So the research question here was, do Michigan students have a lower GPA than the US average? Because our Monitoring the Future dataset is from the US. So we have our average for the sample, which is 3.11, and we compare that against the average US GPA, which we know to be 3. And when we do the test, we get first this one sample statistics descriptives table, which just shows you the sample size, average, standard deviation, and standard error average for your variable, and then does the test against the population mean that you're testing it against. So this bit here that says test value, that's the population average that we gave SPSS that we're testing against. And SPSS then calculates a t-statistic for us and its degrees of freedom. And then this third column of numbers here that's labeled sig, two-tailed, that's the significance value, right? So the p-value, the probability that what we're seeing is just the result of chance or error. And it says less than 0.001. So that means that we can reject the null hypothesis. So there is a significant difference between our sample of students and the national average. And then this fourth column of numbers here, the mean difference, that gives us just how large that difference is. So on average, Michigan students have a GPA that is 0.11 higher than the general student population. And we're 95% sure that the true value lies somewhere between 0.08 and 0.15. So this is that 95% confidence interval. The other thing we get here in this last table is the effect size. So the one that we're going to use and report is Cohen's d, right? We've heard that one before. So how large is this effect that we found that we're reporting? Now you want to look at the second column of numbers, not the first one, the second one where it says point estimate. This is your actual effect size, and it's 0.168. If you'll remember from, or you won't remember it, but if you'll refer back to last week's PowerPoint slides where I listed all of the effect sizes for you in the table, you will know that this indicates that there's just a small effect. So even though, yes, we've got a significant difference between Michigan students and the general student population in the US, that effect is actually quite small. So it's not very meaningful. And the way that we write this up in APA formatting is like this. Michigan students' average GPA was tested against a national average using a one-sample t-test. So here we're explaining what we did, and then we explain the results. Michigan students' scores are on average 0.11 higher than the national GPA, a statistically significant difference. And here I present my t-statistic, but first I put the degrees of freedom in parentheses, and then the actual value of the t-statistic. Then I put the p-value, p is less than 0.001, and then I say with a small effect size. And then I present the actual value of the effect size. So all of those three tables of results, all they equal to is basically 2 sentences. So you will notice that a lot of statistical results are presented in exactly the same way. And in the sample papers I present you with this week, you'll notice that as well, that it's just the sentences are very similar in the sentence structure because there's basically just a few correct ways of wording this information. So what you are allowed to do in this course is literally copy this sentence, paste it into your own paper, and then switch out the variable names that you actually used and the numbers that you used. It is not considered plagiarism just because the way that we present this information is very prescriptive. All right. Okay, next type of t-test is the independent samples t-test. So this is where we're going to compare two different groups. For instance, we might compare men versus women or professors versus students. And the hypothesis being tested is that the two population means are going to be equal, or our alternative hypothesis is that the two population means are not going to be equal. And there are two major assumptions that have to be met, as I mentioned. So you have to have that normal distribution of the sampling distribution for each of your groups, so both for professors and students. And the variance between the two groups has to be roughly equal. So what, as I mentioned, is known as homogeneity of variance. And if you want to remind yourself about these two assumptions, make sure you check out the notes section of my slides. All that information is written in there. All right, let's look at an independent samples t-test example. So here we've got the question of who's smarter, cats or dogs. So what they did was they compared the scores of cats and dogs on a few problem-solving tests. And what they found is that for some things, the average score for dogs was significantly higher than the average score that cats got. But for some tests, it was the opposite because, as we all know, cats are clearly smarter than dogs. They just don't want to show it because they are just like that. And now let's look at an independent samples t-test using our actual data from the Monitoring the Future dataset. So suppose we ask the research question, is there a difference in GPA between students who have tried alcohol and students who have not? What we're going to get from SPSS first is this group statistics output. So just like how for the one samples t-test, the first table showed us the descriptive information for our variable, now it's going to show it to us divided by the two groups. So those who have never tried alcohol and those who have. And we can see that we've got approximately 366 people in the no group and over 1,000 in the yes group. The GPA averages are next, so 3.26 for the no alcohol group and 3.07 for the yes alcohol group, along with their standard deviations and standard errors. The following tables are where we start checking some of our assumptions. So, as I mentioned, unlike the one sample t-test, the independent samples t-test has that assumption of equality of variance. So we have to check that before we look at our actual t-test results. So the first two columns of numbers are that check for the assumption of equality of variance, and that's done through Levene's test for equality of variances. So Levene's test uses what's known as the F statistic, and we'll see that in a second when we cover ANOVAs. But we can see here with this SIG column, so the significance value or p-value, that it's at 0.611. So that means there's a 61% chance that any significant difference between the two groups in their variance is just due to chance, right? So we can conclude pretty safely that they do have equal variances, and our assumption has been met. So if our assumption is met, we read the first row of numbers. If our assumption is not met, so if in Levene's test that significance value is less than 0.05, we have to read the second row of numbers, and it's labeled for you, right? Equal variance is assumed, so yes, assumption met, read this row. Equal variance is not assumed. Assumption not met, you have to read this second row. So our assumption is met, so we can read and report just the first row of numbers. Here's our t-statistic, here's our degrees of freedom, and our significance value for the t-statistic, which is less than 0.001, and then the mean difference that we're looking at for these two groups. So we can say with relative certainty that yes, there is a significant difference between those who have tried alcohol and those who have not. What is the effect size of this difference? We go to our third table, which shows the Cohen's d, that effect size that we talked about. And again, you're going to want to read the point estimate, not the standardizer, which is in the first column, the point estimate in the second column of numbers. And here it's 0.283. So that equals to about a moderate effect size. So the way that we would write this up is that an independent samples t-test was used to test if there was a significant difference in average GPA between students who have tried alcohol and those who have not. The results indicate that students who have tried alcohol have a GPA score 0.19 less than students who have not tried alcohol. So this is where I'm reporting my mean difference. And then in parentheses, I gave the actual t-statistic here, 4.65. And again, the degrees of freedom have to go right after the t-statistic. And lastly, it's that significance value at the end. And then I comment on my effect size. The effect of alcohol on GPA was moderate, and I provide my actual effect size value. The last type of t-test we're going to cover is what's known as a paired samples t-test. So we use this when we want to compare two groups that are related. Most frequently, this is used when you have a pre-test and a post-test of the same group of people. Or you might ask the exact same questions of twins or couples or a parent and their child. And the null hypothesis for a paired samples t-test is that the mean difference, that's what this mu with the little d means, that the mean difference between the two groups is going to be 0. So basically that there is no difference between the two groups. The alternative hypothesis is that the mean difference between the two groups isn't 0. So there is some kind of difference between the two groups. The only assumption for the paired samples t-test is that there's a normal distribution of different scores. So the difference between each person's pre and post test score, if you were to map them out, they're going to have a normal distribution. Unless the sample size is large enough, as we know from the central limit theorem. In general, your sample size is going to be large enough, so you don't have to worry about this assumption. And that's exactly what you would write in your paper, just that the sample size of, say, for monitoring the future, we've got more than 1,400 students, is sufficiently large that any deviation from normality is not going to impact our test results. That's all we have to say. All right, let's look at a paired samples t-test example. So my favorite is the use of puppy rooms. You have a stressed group of students taking a statistics class, you measure their anxiety, then you let loose 10 puppies for them to pet and cuddle with for an hour, and then you test their anxiety again. That's an example of a paired samples t-test. So we expect that your anxiety scores are going to drop after you've had a chance to play with a bunch of adorable puppies, unless you have a phobia of dogs, in which case you're going to be that one outlier that's going to have a much higher anxiety score. But in general, we delete those outliers because they mess up the data. All right, here's an actual example using the Monitoring the Future data set. Because the Monitoring the Future data set actually is just a cross-sectional data set, it doesn't have 2 points in time or any kind of data that we can use for an actual paired samples t-test. We're just going to pretend that the variable police job performance and the military job performance variables are really pre-test and post-test scores after a visit from a police liaison. I mean, they're not, but we're just going to pretend they are for the purposes of seeing what a paired samples research question and output looks like. So our research question here is going to be, was there a significant change in students' perception of police job performance after the police liaison visit? So we'll say police job performance is the pre-score and military job performance is the post-score. As with the other types of independent or t-tests, the first table is always going to be that descriptive statistics table that shows you the average for that variable, how many students answered that question, and the standard deviation and standard error. The next two tables give you those actual results. And again, you've got the mean difference. You can see here that this table is called paired differences. So this mean here, that's the mean difference. And it's taking that time 1 minus time 2. And giving us a negative 0.802. So that indicates that between time 1 and time 2, there was an increase in scores. If there had been a decrease in scores, then this number would be positive. And for the paired samples t-test, the t-statistic is actually at the end of the table. Whether the t-statistic is negative or positive doesn't matter. That just indicates where on the t-distribution it's located. What is most important is the significance value. So again, it's less than 0.001. So there is a difference between the trust in police scores before and after a police liaison visit. And then we always want to check our effect size to find out just how big of a difference we're talking about. And again, we only report this Cohen's d, the point estimate right here in the second column of numbers. And again, when it comes to effect sizes, whether the value is negative or positive doesn't matter. It doesn't make a difference. It's still the size of the effect that's important, not the direction. So 0.644 is the effect size we're seeing here, which if you look at the table from last week, what you will know is a large effect size. So the way we would write this up is by saying a paired samples t-test was used to determine the effectiveness of a police liaison visit in changing students' attitudes towards the police. There was a significant improvement in the students' perception of the police after the police liaison visit. So you can see now I put the mean difference in parentheses as opposed to in the sentence. In my mistake, but this MD should be italicized. Then I put in the degrees of freedom and the T statistic and its p-value. The police liaison visit had a moderately large effect on students' perception of the police, and then I report the actual effect size value. So why am I saying moderately large here? It's because the effect size is halfway between a medium effect and a large effect. So that's where things like moderately small also come in. When you're halfway between two general cutoffs, you just stick in the word moderate. All right, so the last type of statistical test we're going to look at today is what's known as analysis of variance. But this is actually a large family of tests. And we're just going to look at the simplest one in this class. But if you understand the simplest one, you can understand all of the more complex ones. So what we're going to look at is the one-factor ANOVA, where there's one independent variable and one dependent variable. But what you're going to come across a lot more commonly in the literature is the two-factor ANOVA and the three-factor ANOVA. So that's where you still have that one dependent variable, but you're able to account for multiple independent variables. And three-factor ANOVA, that's telling you that there's three independent variables that you're looking at. And this allows us to compare for an independent variable with three or more groups, whether there's significant differences on a continuous dependent variable. So you might think to yourself, why are we using an ANOVA when we could just use a series of t-tests? And the reason for that is math. If we just do a series of t-tests, for each t-test, we're going to have type 1 error of 0.05. And that's for each one you run. So the more tests you run, the more your errors add up. And with ANOVA, you don't have that problem. It's able to, for the entire test, have just a type 1 error of 0.05 instead of added up across all of the comparisons between the individual means. We've also got what's known as an ANCOVA. So besides the independent variable and the dependent variable, this is where you also control for a continuous covariate. So a variable that you assume is going to vary with the dependent variable in some way. It's going to impact it. So if we were to do some kind of mediation analysis, we would stick in a covariate. Don't worry, you won't be doing this, but I just want you to be able to recognize what this means if you see it in the research literature. And MANOVA stands for multiple analysis of variance. So this is where you have several independent variables as well as more than one dependent variable. So for instance, this is something that you might use when considering an intervention that addresses people's depression. You might want to measure not just their depression scores, but also their anxiety scores as well, so that you are able to see whether your intervention has an impact on either depression or anxiety, while also accounting for any correlation or effects that they might have on each other as dependent variables. And then most complex of all, we've got ANOVA, where you've got multiple independent variables, dependent variables, and covariates. And we can also use this the same way that we use a repeated a paired samples t-test. We can do it with a repeated measures ANOVA. So either we're looking at, 3 or more points in time, or 3 or more related groups, like a parent rating, teacher rating, and a child's rating of the child's anxiety. That would be using what's known as a repeated measures ANOVA. But let's focus just on the one that you need to be able to do for this class, and that's the one-factor ANOVA, also known as a one-way ANOVA or a between subjects ANOVA. It's where you have one independent variable that's got 3 or more categories and one continuous dependent variable. The null hypothesis looks very similar to that independent samples t-test, right? It's just we've added a third mean to that or more if your independent variable has more than 3 categories. On the other hand, the alternative hypothesis is going to be that at least one group mean is going to be different than the others. And the ANOVA is tested with what's known as the F ratio test because it uses an F distribution. So we've got a few assumptions that have to be met for an analysis of variance. As I mentioned, you're going to need a normal distribution of the scores unless your sample size is very, very large. And you have some assumptions about the variance. So making sure that the variance between your groups is going to be equal, otherwise known as homogeneity of variance. And I'll show you how to test for both of those. All right. So here is an example using I'm monitoring the future data set. Is there a significant difference in students' GPA based on their levels of happiness? So the first table with an ANOVA is what how our score groups are distributed. So we've got 3 levels of happiness: not happy, pretty happy, very happy, and how many people are in each of those. And then the next table is the actual results. Now, I know this is very, very complicated, but there's just a couple things that you need to focus on here, and that's this here, where it says happy, that's your variable. That's the only row that you need to examine. So happy has an F statistic of 26.29 and a significance value of less than 0.001. So we can say that, yes, there is a significant difference in people's GPA based on their level of happiness. Now, the effect size is also given to us in this table. And for ANOVA, the effect size is called partial eta squared. So you need to report this number here in the last column, 0.036. And if you look at that table I gave you last week, you'll know that this is a moderately small effect size. So the cutoff values for eta squared are different from Cohen's d. The thing that this table doesn't tell us is which happiness levels differ from which ones and how much they differ. So we know that there's a difference somewhere, we just don't know where. And that's why we have a third table that we get from our ANOVA results, and that's the post hoc tests. So post hoc means after the fact. So if we get a significant F statistic, we read the post hoc test to find out exactly where a significant difference is. If it's not significant, then we don't need to read this table because we're not going to see any significant effects. Now, what this does is it compares each level of happiness against each of the other levels and gives you the mean difference between the two. So the first row is comparing not happy people with pretty happy people and finds a difference of negative 0.2867. So what that means that on average, not happy people have a GPA that is negative 0.286 lower than pretty happy people. Because as you can see here from the mean difference column, it says I minus J. So it's taking that I column minus the J column. So not happy people minus pretty happy, whatever their GPA scores is going to be negative 0.2867. So indicates a drop. Not happy versus very happy, negative 0.45. So on average, not happy people are going to have a GPA score that's almost half a GPA score less than very happy people. And if we look at this significance column here, we can see that those are significant, statistically significant findings. What you're going to see that it does these comparisons for each possible combination. So by the time you get to the end, you're comparing very happy with pretty happy, which you already compared before. So you don't need to report all of these. You only need to report the significant ones and just the ones, right? Because this very happy with not happy is giving you the exact same value as up here, just without that negative sign because of the way now we're taking the GPA of very happy people and minusing the not happy people's GPA to get a score of 0.45. All right, so we're going to report all of the statistically significant pairs of differences, and for this table we see that we have 1 for not happy versus pretty happy, 2 not happy very happy, and then 3 pretty happy and very happy. So 3 different pairs that we're gonna compare. The other 3 are just repeats of what's already been reported in the table. Our write-up is going to be a little bit longer than anything we saw for the t-tests. So we start off by explaining what we did. A one-factor ANOVA was used to test differences in student GPA based on their level of happiness. And then I report my overall findings, that there was a significant difference in students' GPA based on their level of happiness, and I give those F statistic results. You can see here with the F statistic, we've actually got 2 degrees of freedom that we need to report. The first is the degrees of freedom for our actual variable, and the second is the degrees of freedom for the error. And I will show you where to find those in the SPSS practice video. Then we give our actual F statistic and its significance value. The effect size was moderately small, partial eta squared, and this here is the Greek character for eta, and the little 2 indicates it's squared, and I give the value here. Not happy students had an average GPA 0.29 lower than pretty happy students, and I report this standard error and the significance level, and then I do the other comparison too. And 4.5 less than very happy students, and again, standard error and significance value. Then I report my last and third pairing, which is pretty happy students had an average GPA 0.16 lower than very happy students, again with my standard error and significance value in parentheses. To see how others write this up, I have included an article for you in this week's lecture. It is looking at shared pain as a way of increasing cooperation between students. I thought it was a great example because you all going through this class are experiencing this shared pain, which can increase your social cohesion. Anyway, this article gives you an example of how independent samples, t-tests, and ANOVAs look like when they are written up. You don't have to read the entire article, just use it as a reference of what it looks like when it's written up and to test your knowledge to make sure you understand everything that I just explained in this lecture. If you're still not completely understanding the article, have a watch through the lecture one more time. The last thing I want to cover is how to report that significance value. So if the p-value is between 0.01 and 0.049, we report it as p is less than 0.05. All right? If it's between 0.001 and 0.009, we report it as p is less than 0.01. If it shows up in your SPSS output as 0.000, SPSS isn't actually saying that your significance value is 0 and that there's absolutely no chance you've committed a type 1 error. It's just that it's a very, very small value and it doesn't have enough space in the column to indicate that. So that's why every time we see 0.000, we report it as p is less than 0.001. If the p-value is not statistically significant, so if it's equal to 0.05 or higher, we either write the p and then the exact value, or we can put ns for not significant. So what that looks like written up is like this, ns or p is equal to 0.15. All right, that's it for today. Have fun running these tests in SPSS.